Since we didn't have tons of time in class, I wanted to spend a little bit more time going over some of these rate law experiments to figure out this method of initial rate. So I'm pulling these right out of section 1.4. So first off, the sample problem. So they've worked it all out for you with the math, but I do want you to notice that in this problem there are 1, 2, 3 reactants listed. You've got the rate here in the far right column. Sometimes we see it on the left. And here they're listed as runs, but again, these are still trials or experiments or whatever it is you want to call it. So that's what you're looking for. So first off, let's try and figure out the rate with respect to this bromate, this BrO3 minus. So in this instance, if I look at trials 1 and 2, the bromate increases by a factor of 2. The bromine is constant. The H plus is constant. And if I look at this rate, well, going from all those zeros 80 to those zeros 160, that is also increasing by a factor of 2. Same factor, so it is first order. But how would I write that up? I would say that in experiments 1 and 2, Br minus and H plus are constant. Bromate, BrO3 minus, increases by factor of 2. Rate increases by same factor. And then mathematically, that is 2 to the x equals 2. So x equals 1, first order. All right, so I'm going to change colors for you. Now let's look at the bromine. So if I'm looking at the bromine, I need a situation where the bromate and the H plus hold constant. And I can see that in experiments 2 and 3, again, bromate is constant, H plus is constant, but I increase by a factor of 2 here, and I look, and I'm going from essentially 16 to 32, I'm also increasing by a factor of 2. So the bromine is first order. And I would write almost the exact same thing, right? So in experiments 2 and 3, bromate and H plus are constant. Bromine increase by factor of 2. Rate increase by same factor. 2x equals 2, so x equals 1, first order. So I've done it for those two. I still need to do it for the hydrogen. So I need to look for an opportunity where my bromate and the bromine or bromide are constant, but the hydrogen is changing. Now, sometimes this is a little bit harder to find, but what I see here is in experiments 1 and 4, that is constant, that is constant, that is increasing by a factor of 2. And if I look here, I see an 8 and I see a 32 that is increasing by a factor of 4, which is the factor squared. So that is a 2. So how do I state this? I'm going to say in experiments 1 and 4, bromate and bromide are constant. H plus increased by a factor of 2. Rate increased by factor squared. 2x equals 4, so x equals 2, second order. Okay, So typically they're going to ask a series of questions that all kind of sound the same. So let me move this up a little. So I've got all this. Okay. So often the first question you get asked is write the rate law. So my rate law here would be rate equals K, brackets the bromate to the first, the bromide to the first, the H plus to the second. Then they often ask you for the overall order. The overall order here is simply adding those exponents together. So that would be 1 plus 1 plus 2 for an overall order of 4. Then they often ask you for the value and the units on the rate constant. So this is where I said you basically pick one of the trials and plug your numbers into the rate law. I don't know why people pick anything other than trial 1 in these things because I think it's strange. But if I do that, I get 0.0080 is my rate, even though it's on the right side of my data table, it's on the left side of my formula. I am trying to solve for K, so I'm going to put it in a different color to make it a little easier to spot. And then I need to plug in my concentration. So in trial 1, all of those are 0.10. So the bromate is 0.10 to the first, the bromide is 0.10 to the first, and the H plus is 0.10 squared. So do not mess that up. So that means that my K is equal to 0.00080 divided by 0.10, and I've got 4 of those, right? That is raised to the 4th power. So if I do that, plug it into my calculator, 0.00080 divided by 0.10 to the 4th power, and I get 8. Simply an 8, which makes sense. Okay, so that is the number, but I need the units. So here's the thing. This rate up here is molarity per second. Now, that's not the way they wrote that, but you know that mol/L is molarity. So this is molarity per second. And down here, each one of these was a molarity, so that means down here, that is a molarity to the 4th. So here's how you need to look at this. I've got a molarity per second, and I am dividing by a molarity to the 4th. So what happens there? Well, that molarity goes away, and this one gets knocked down to a 3. But these are both denominator values. So I simply write S to the -1 and M to the -3. And that should make sense because it is 4th order, which means there's 4 molarities on that reactant side, and then I'm going to take all of those away. Okay, so that's the sample problem. Let's see, let me go through another. All right, so this is one of the first practice problems. It says use the information in the table below to write the rate law expression. All right, so basically all the same thing. So notice that they didn't give me actual rates here, but they did give me things that actually make it a little bit easier because they just straight out tell me how many times the factor increased. So let's look at this. So I have O2 and I have NO. So if I look at experiments 1 and 2, my O2 stayed the same. My NO increased by a factor of 2. My rate increased by a factor of 2, which is the same factor. So I would say in experiments 1 and 2, concentration of O2 was constant. NO increased by a factor of 2. Rate increased by same factor 2x equals 2, so x equals 1, first order. Boom, there's a 1. Okay, so now I need to pick a set of experiments wherein O is staying the same, but the O2 is changing. So I've got two different options here. They're not exactly right next to each other, but why don't we pick 1 and 3, because in O is constant. The O2 increases by a factor of 2, and the rate increases by a factor of 2. So then I would say same thing in experiment 1 and 3 in O was constant. Concentration of O2 increased by a factor of 2. Rate increased by same factor. 2x equals 2, so x equals 1, first order. Okay, so what is my overall rate law? Well, it is rate equals k, O2, and in O, both raised to a 1. This is second order overall. And let's see if we can't figure out the rate constant. So let's pick a set of values. Let's pick the first one. My rate is x, so this is going to be weird already. Leave my k in a different color to make it easy. Concentration of O2, I'm going to say 0.0010. That's raised to the first. My NO, 0.0010 raised to the first. So k is basically x over 0.0010 squared. That's going to give us a number. 0.0010 squared. Let's see if that's on the bottom. So k is actually equal to 1 times 10 to the positive 6, since that's going to be a negative down there, x. And if I look at the units, well, rate, again, I see is in molarity, S negative 1. Each of my concentrations are in molarities, so I've got a rate that is molarity to the S, and I am dividing by a molarity squared. Cancel. That cancels, so my constant here is going to have units of S negative 1, M negative 1. And that's how we are doing those initial rates.